So today, tomorrow, and Friday, I believe too, we will be examining some different ways of graphing in the coordinate plane. Okay, some different ways. All right. Today it's going to be not too. Whoops, I want this in there. Today it will be not too crazy. It's going to be like a little baby step away from our very comfortable, very usual way of graphing things with an x coordinate and a y coordinate, because there's still going to be x's and y's in there. We're just going to throw in a third variable called the parameter, and you'll see what I mean by that in just a second. But then tomorrow and Friday we're going to be looking at a way to graph in the coordinate plane that changes the foundational way that we use coordinates, right? So typically, right, when we graph in the coordinate plane, we use x and y. X tells us whether we go left or right, how many, right? And then y tells us whether to go up or down, that many, right? So we're going to change that fundamental definition of coordinates in the coordinate system and create a completely different kind of graphing system called polar, and we'll talk about that tomorrow. So that's it's kind of cool. You get some really interesting kind of graphs by changing the way that you define things. But right now we're going to take the little baby step of the parametric equations, okay? Which again, I think we kind of lump parametric and polar together. They are related, but they're not the same thing. So it's not like necessarily they lead right into the other, but they're related because they're different kind of ways to graph. So we are familiar with equations, with one equation that has two variables. Okay, when it comes to graphing, or just when graphing, I'll say. Okay. And some examples of those, right? I mean, that's what we just did for the warm-up, right? So we saw like, okay, y equals 2x minus 3, y equals x squared minus 3. Okay. And we're very comfortable with that, right? The x is typically known as the independent variable, right? The independent variable. So that means we kind of we select the values for x, and then we kind of input those x values as the independent variable, and then the y values we get as a result, the output. The y values tend to depend on those x values, right? So sometimes, okay, we have need of a third variable t. Okay, and we write x and y as functions of t. Okay. And we use letter t because typically t is going to represent time. So we're introducing this third variable t, and then we're going to basically rewrite x and y not as relating to one another necessarily. We're going to rewrite x and y as relating both to time. Okay. So traditionally, when you graph things, right, you graph things maybe with like, if you're talking about like the projectile motion, like you're throwing a ball up into the air, you can only graph either the height versus time or the distance of that ball versus time. You really don't graph the height versus the distance. Sometimes you do, but most of the time it's one or the other there. So here we're going to be able to take both things into account though. Like x might be the horizontal distance with respect to time, and y can then be the vertical height with respect to time or something like that too. So those kind of deals. Okay? So that's the idea here. So for definition, all right, we'll say that x then equal to f of t and y equal to g of t. Okay? These are parametric equations. And so now x is no longer an independent variable, it's a dependent variable. X depends on time. Y still remains a dependent variable, it also depends on time. Our new, or the t, I shouldn't say time because t can be different things, but our parameter there, t. And now t is the independent variable. So t is the parameter and x, y, or f of t, g of t, okay, is an ordered pair on the coordinate plane. Bless you. Okay. So, we're going to start just like how we always start in mathematics with this kind of graph. If we're going to try and graph things here, we're going to start graphing using a table. Okay? So first we want to be able to graph these things. Okay? So there's our parametric system right there. Okay, there's our parametric system. Our x-coordinate of our point in the coordinate plane is going to be defined by x equals t squared plus t. Our y-coordinate will be defined by the function 2 times that same t value plus 1. Okay? And so when we go about graphing this, it's the t values that we'll be kind of choosing here. So I'm going to make a table, and for, we'll say from like -2 less than or equal to t less than or equal to 2. So we'll just keep the t values between like -2 and 2. Again, you can pick whatever t values you want. You can pick whatever t values you choose here, but I'm just going to pick some smaller t values, close to 0 and stuff like that. All right, so I make a chart. I'm going to make a horizontal chart instead of a vertical chart, just to save on space, I think, is the idea. Okay, so if I'm making a table for -2 to 2, that means I want my t values to be like -2, -1, 0, 1, and 2. Okay. And again, you absolutely can do fractions, right? There is such a thing as a fraction of a second if we're thinking again in parameters, parameters time. So I mean, you absolutely can do like t equals 1.5, t equals pi. You can do that. Okay. So if t is, let's do a 0 first. 0 will be easy. 0 is an easy one to start with here. So if t is 0, what's our x coordinate? What's our x coordinate going to be when t is 0?
0.
Yeah, 0. How did you get that?
You plug 0 into t.
Yeah. I mean, that's all there is to it, right? If x is defined by t squared plus t, if t is 0, well, it's be 0 plus 0. So it's just going to be 0 as well. Okay. What's going to be our y coordinate when t is 0? 1, right? Again, same reason. 2 times 0 is 0, plus 1 is 1. Okay. And so we can fill in the rest of the table in a similar fashion. I'll go to the positive numbers and we'll do the negatives here. So starting with 1, t is 1, so it's going to be 1 squared, 1 plus 1, so that's 2. And then 2 times 1 is 2, plus 1, it'll be 3. And we'll do 2. 2 squared is 4, plus 2 is 6. And then 2 times 2 is 4, plus 1 is 5. Okay? And then let's try -1. -1 squared is 1, plus -1 will be 0. Okay? And then y equals, so 2 times -1 is -2, plus 1 is -1. Okay? And then x, if t is -2, then -2 squared is 4, but plus -2 is going to be 2. And then -2 times 2 is -4, plus 1 is -3. Okay. So, we have an interesting situation happen here already, something different, all right? If we were to graph the x and y coordinates here, will the graph of this thing be a function? Will the graph of this thing be a function? And if not, why not? I see some no's. So why isn't this thing going to be a function? What's happening? Yeah, Nick?
There's two y values for the same x value.
Yeah, two different y values from that same x value of 0 there. So we're going to end up with something that's not a function. I mean, this thing is not going to pass the vertical line test. Whoa. We typically don't graph a lot of things that aren't functions, right? Most of the stuff that we graph, they're functions, right? They pass our vertical line test. So what's this thing going to look like, right? Well, let's put these coordinates together here. So we've got the coordinates 2, -3, 0, -1, 0, 1, 2, 3, and then 6, 5. Okay, and I guess the x value 2 also is repeated there as well. X value 2 is repeated too. All right, let's sketch this thing. So I'm going to go over here and just draw a coordinate plane.
Wait. Oh, I already did one.
So we can still use our coordinate plane to graph this, and we still will use our coordinate plane to graph this, which may be kind of confusing because we're taking something that has three variables, and we're graphing it two-dimensionally. We're taking 3 dimensions, t, x, and y, and we're going to graph it only two-dimensionally, right? Only using an x and a y there. Okay, and I'll show. We are going to label the t as well, and you'll see kind of how that looks here in a second. Okay. So, question? What's this for? So to it is typically used to describe things like particle motion. It's a handy or like motion of objects and stuff like that, horizontally and vertically kind of thing. So with respect to time, so you can think of like, if you're like looking down on top of something, if you want to see like shift roots or something like that, you can see like shift roots, but then you also know at what time they're at what point kind of thing too. So for if you're trying to manage like or even flights too, if you want to know like if a plane will hit each other, or like if flight paths can't intersect as long as they're not there at certain times and stuff like that. So there is application for this for sure. So anyway, let me get some coordinates here. Okay, so let's plot these points. So 2, -3. Okay, there's that point. Oh, thank you. And then 0, -1, and then 0, 1, and then 2, 3, and then 6, 1, 2, 3, 4, 5, 6, and 1, 2, 3, 4, 5. Something like that right there. Okay. So there's the curve, and we want to be careful about how we graph this, right? We can't just connect these dots however we want. Normally, right, when we connect the dots, we just go from left to right, right? We just go from left to right and kind of connect things. But here we can't really go from left to right. That's going to result in a weird-looking graph. Instead, you want to connect the dots according to the time. So in addition to these points here, I'm also going to label at what time or what the parameter was. So I'm going to say, okay, at that dot it was t equals -2. This dot was t equals -1. This dot was t equals 1. This dot was t equals, oh, that was 0, I should say. Bless you. T equals 1. And this dot was t equals 2. Okay? And that's how we kind of take care of that third variable, right? How we label that third variable in here. We kind of just label those points. And now we're going to connect the dots in order of time. So, and again, try and make it kind of a smooth curve here. So, okay. And you can kind of like extend this back here some too. All right. Now, because as t is advancing, as our parameter advances from negative to positive here, we want to indicate that kind of gives an idea of a direction as we're kind of flowing forward in time, maybe, or something like that. So it's typical to also draw little arrows here along the curve to show the direction. The orientation, actually, is the official word for it here. The orientation of the curve, which is really just the direction or movement of the path. Okay, the direction or movement of the path there. Okay? So there it is. That's how we graph a parametric equation. Okay, that's the graph of a parametric equation. And of course, the sky's the limit for the kinds of graphs that you can create, because again, it's all defined based on x and the y. Now, of course, playing this by hand is kind of tricky because you have to then make the table and then plot all the points. But guess what? Our graphing calculators can do this too. All right, so let's use these little fancy tools here. All right. So first of all, if we go to try and graph, I got some junk in there from another activity. If we go and try and graph, we can't graph parametric here. these are all y equals, right? But we have like, well, we do kind of have a y equal here, but we also need to graph an x equals too. So we're going to press the mode button, okay? And if you look there, right now, the y equals is because our mode is set to function. But if we want to graph parametric, guess what we want to go to? PAR, okay? And so we're going to go to y equals, which now has changed. What? Okay. We now have, if you look here, with every line, we have two things to graph, x and y, right? And then the next one is x2, y2, the next one is x3, y3. So now we can actually plot these things in our graph. Now, our parameter is supposed to be t. What do we press? The same button we always press. But now it becomes t when you press it because we're, in the parametric.
What button did you press?
The normal x, like, hello? Hi.
Is it the one with
Under
like
mode.
X, comma,
Okay, no problem.
comma,
Bye.
yeah.
Ralph, they want you down at AP office, in AP office, for something.
I'm not doing this too. No, I have one.
Oh, you just want to do it?
Just don't assume that I didn't bring it.
Well, I assumed that you didn't because you're asking myself, so. Question? No? Okay, so we can graph this. T squared plus T. So you're just going to be a party pooper list, is that what you're saying?
Yeah.
You're not impressed? Alright, fine. So you also, so if you go to graph, whoops, my thing is way messed up there. You'll see this. So yeah, it should be 2t plus 1 and then t squared plus t. So there it is. Which doesn't look like what we have. But it looks kind of like what we have, maybe. But if we go to the window, you'll notice here other things have changed about the window too. We now have a t min and a t max. Okay? What was our t min and t max for our graph? -2 to 2, right? So if we want to graph like the way we graph, then we need to go -2 to 2, okay? And then also you'll see here there's a t step. What was our t step? 1. And so I'm going to make that 1, okay? And I'm also going to change the x min and x max. Mine kind of went from like -6 to 6. Well, maybe we'll keep the -10 to 10 and we'll see how that looks. And so there is a better picture, all right, for our graph. Okay.
Wait, so T max to
So go back to window here, sorry. T min, -2 to 2. T min, T max, -2 to 2. T step, 1, because they're counted by 1s. Okay. And then the window should be still your normal, -10 to 10, -10 to 10 for x min, x max, y min, y max. Let me graph it. And there it is. Okay. Now, if you hit trace, you'll see here that we start at the -2, and there's our x coordinate 2, y coordinate 3. And if you press the right button on your arrows here, okay, the calculator moves to the left. Why? Because that advances. When you press the right direction arrow, it's advancing to the next t value, t equals -1, and so the next t1 is to the left. So you press right again, and again it jumps then to now the t of 0, t equals 1, t equals 2. Okay. And of course, if we wanted to extend this graph, we could go to our window and make it like -20 to 20. Right? So you could increase the t interval there to get more of the graph. And so there you can see it's essentially, well, what kind of shape is this? It's like a parabola basically that's been reflected over the x-axis. Okay, it's essentially like a parabola here. Or reflected over the line y equals x, I mean, it's a parabola.
I don't know what it's called. Wow, you're cool.
So. All right. So there's like your graphing calculators, and of course then now that opens up all sorts of possibilities. I mean, you could do all sorts of different things to see what happens when you mix and match different kinds of functions, right? And see what kind of results you get. Sometimes you could even throw in let me just try doing something strange here and see what happens. Let me try cosine. All right, I gotta do it this way. See if we get anything weird from that. Okay, that is very weird. Okay, so I don't know if that helped or not, but anyway. Yeah, no, that didn't help. I'd have to think about that some more. I may be not doing things well here, but okay, anyway. So you can mix and match and stuff like that. And you can graph things, okay? And then of course then tomorrow you'll see here we have also then the polar waiting for us tomorrow, so we can like mess with that too. So SEQ sequence. You can actually do sequences on there as well. Why don't we use the calculator for that? Because I don't know how to actually. I have to play with that one some. I don't know. All right?
Mr. Rizler,
Yes.
in the window, what's T-step?
What's T-step?
Yeah.
So T-step is like, you can kind of think of it, in my understanding of it, it's kind of like the resolution for your graph. So it's like the number of calculations that your calculator will do in those from negative 20, for example, from negative 20 to 20. So for example, I could have it take a step of 20. Let me go back to like the negative 2 to 2, and instead of having it take a step of 1. So well, you saw what 1 looked like. Oops, I changed my other thing too. So what was it? T squared plus t, I think, right? Okay. So there's that. If you change, and I think, let's see here. So that's the t step with 1. If I change it to t step of 2, you see what it's doing now here?
Go every 2 values.
So exactly. And so what it does, it kind of like it doesn't give you as fine of a graph. It doesn't like graph enough points for it to get a nice smooth curve there. So it kind of like approximates it. So it creates that kind of sharp thing. Now let me try going by like 4s here and see if it makes it even like oops, let me go by 4s, see if that makes it even worse. Yeah, it just connects the starting point and the stopping point kind of thing. So the more
Point to let it go smoother.
so right. So I think so when we did 1, we got what looks like it should be just the curve there. So we're probably pretty good there. But if we did like 0.1, let's try that. It just takes more time to calculate more points. I think the idea is you're trying to strike a balance between having enough points where you get the right idea of the curve, but also not having so many that the calculator labors under the intensity of all that calculations. Because I think if you did something like, let me try to break the calculator here. Okay, so it doesn't like that. It gave me an error because it would have been calculating way too many points, kind of thing. So let's see if I can get it to. You can see how slowly it's graphing that because it's calculating like thousands of points. So that's the idea. You're trying to strike a balance between getting an accurate graph, but also then, not having too many points there. So we'll just let that run for a little bit and come back to it later. All right. So anyway, so that's how you graph these things. I'm going to move on though because there's other things we got to talk about too. All right. So of course, a graph that we just saw there, that's a graph of something we've seen before without using parametric equations, right? We've seen, well, you can do it, little guy. All right, so there it is. We've seen stuff like this before, where it's like a parabola on its side, and so we can potentially then convert that into rectangular coordinates. What's that? I know, yeah, it takes some time. Yeah.
How big is it? What's the number?
I think it's like 1/1000th. So it's having to calculate all the t values from negative 2 to 2, counting by thousands. What's that? Yeah, it's like having a lot of calculations it has to do. So that's why it's creating so many of those. Okay? So, we'll talk about eliminating the parameter. Sometimes we're able to do that, sometimes we're not. Okay? Eliminating the parameter. So let's say we've got x equals 2t minus 6 and y equals 4t plus 10. Okay? We are currently in parametric, and we want to convert from parametric to rectangular. Rectangular is the coordinate system that we denote for the xy, coordinate system, okay? Or just the straight up xy without the t. So essentially we want to get rid of the t. We want to eliminate the t. Okay? Very similar to what Andrew had us do earlier when it comes to solving the system. Okay? So what we're going to do is solve one equation for the parameter t in this case. Okay, I'm just going to pick the x one here. So we've got x equals 2t minus 6, and so then x plus 6 equals 2t, and so then t equals 1/2 x plus 3, right? If I divide everything over here by 2, it's just 1/2 x plus 3. Okay. And so then, what can I now do with that 1/2 x plus 3? Where can it go? Where can we put it now to help eliminate the parameter? Where can we put that? Say, Sean, sorry? Back into the original one, in for y. We'll plug it, or sorry, in for y, into the y equation, but substituting in for t. And so that's right. So then, substitute for t in the other parametric equation. Or just the other equation. Bless you. So we have y equals 4 times 1/2 x plus 3 plus 10. Okay, which we could then stop. We now have eliminated the parameter. This is the graph of this thing. Y equals 1/2 x plus 3 plus 10. But of course, we can simplify that, so we might as well distribute the 4, right? So we get 2x, and then 4 times 3 is 12, but then plus 10 will be plus 22. Okay? So in other words, the graph of this parametric equation is the same as graphing 2x plus 22. Graph 2x plus 22, right? And if we were to show that here, let me go back to my calculator. So I'm going to graph 2t minus 6, 4t plus 10. Okay. There's that, and I'm going to change my window, or my... So let's see here. If I know my graph's going to have to be the graph of 2x plus 22, means my y values are going to have to go up a little bit higher than 10. So I'll go up to like 30 there. And I'll make my t-step go back to 1. And let's just try negative 2 to 2 again and see what happens. Okay. Let me do a little bit more than that. Let me say negative 10 to 10. Okay. And so sure enough, there's our graph of our line. Okay. If we, let's see, trace here. Okay, so there's my y-intercept at 22. Okay, you can see that at t equals 3, and the y-intercept is 22. Okay, so there's that. And you can just see that the slope is going to be 2, right? We go from 0, 22 up to 2, 26. Okay, so we went 2 to the right and up 4. So 4 over 2, slope of 2. So that is the equation 2x plus 22. Okay. So there is an equivalent rectangular form. Now, not always, we can't always do this, but in this case, you know, sometimes we can eliminate that parameter and rewrite it. Okay? All right, let's try another one here. Okay, so we're just going to do, after this, we're going to be converting from a rectangular form to a parametric form. So that's, just make sure you guys check out the video, okay?
He's like, after this, she's just...
Yeah, when did she leave?
It's okay. Maybe she didn't realize I was talking to her. That's okay. Okay. So here's this one. T squared minus 4, 1/2 t. Yes.
Why did that cancel out?
Why, what cancel out?
Like, why did it, what did you mean by eliminating?
We eliminated the parameter. The parameter is no longer part of the equation. So we took something that was in a parametric format, and we rewrote it in a format that no longer had a parameter, so now it's just a rectangular format. Okay? So we're going to do the same thing here. Again, another parametric equation. If we look at the graph, x squared, oops, t squared minus 4, and then 0.5t. Okay, I'll go zoom 6 and go back to a standard viewing window. Okay, so there you can kind of see the graph. I'll change my window and adjust things down, go to like -5 to 5. Okay, you can see it's like another parabola, right? But again, it's on its side, right? It's reflected. So let's see what happens here when we try and come up with the equation for this. So we'll do the same thing here. All right. And let's do the x equation. We'll solve it for t. You can again choose either equation you want. So we could solve the y equation for t and then plug in to there. So you can do it either way. Okay, actually, do you guys have a preference which one we do? Okay, so we'll just do the x one again, okay? So we have x equals t squared minus 4, so then to solve for the parameter, we're going to add 4 over. Okay. To get the t by itself here, what do we have to do now? Square root both sides. Now, since we're in an equation setting, we're square rooting both sides, I need to write t equals plus or minus the square root of x plus 4 there. We'll then plug that, excuse me, we'll plug that into the y equation here. Okay, that, which we can then just write, plus or minus 1/2, right? Because it's really like plus or minus 1 here times 1/2. So it's plus or minus 1/2 times the square root of x plus 4. Okay, so there's the graph of it. You can like visually see right there. Now let me change back to functions, and I'll graph the rectangular version, which is going to be a positive 0.5 square root of x plus 4, and a negative 0.5 square root of x plus 4. Okay, we graph it. And there's the same thing, rectangular form. Of course, this graph continues graphing on because it's doesn't have those t values. We only said from -2 to 2, but here it's just graphing the entire graph. Okay, not just the particular t values there. Okay? Now, what if we had chosen to solve for y first, right? What if we had chosen to solve for y first? Well, we have then t equals 2y, right? T equals 2y, if we multiply both sides by 2 there. Then we plug it into here, we would have x equals 2y squared minus 4, which is the same thing as x equals 4y squared minus 4. So this also eliminated the parameter, just like this one did. Okay. Of course, one is solved for x, one is solved for y. So if we wanted to rewrite this in a more traditional, y equals format, we'd have to solve for y here. So you have x plus 4 equals 4y squared. Divide everything by 4, so you have 1/4 x, excuse me, plus 1 equals y squared. Square root both sides here, so we'd have plus or minus the square root of 1/4 x plus 1 equals y, which is the same thing as this right here. Okay, and if you don't believe me here, I'll show you here real quick how we can show that this is the same. If we take a 1/4 out, we're going to have this. Now this is probably the biggest leap you have to take here. All right, again, to show that this is the same as this, I'm going to factor out a 1/4 inside the square root there, right? If I take a 1/4 out of 1/4 x, most of you guys will believe me, it's x. But if I take a 1/4 out of 1, that means I'm dividing 1 by 1/4, we should get 4, right? If I redistribute this 1/4, I'll go right back to where I was there, right? Now, we can break up a square root over a product like this. And what's the square root of 1/4? 1/2. And there it is, the same thing. Okay, so these are equivalent. This is the same thing as this. All right. So that's eliminating the parameter. All right. And then one more thing I'm going to show you, and that is we're going to also create the parameter, I guess. I don't even know what to say. We're going to convert from rectangular to parametric, okay, as well. Okay, and this is probably even easier, okay? So then converting rectangular to parametric. Okay? So the last step. So we can graph parametric now. Just pick some t values, plug them in, get the matching x and y, plot those x and y values along with the t, and then draw the arrows. We can convert parametric system to rectangular by using kind of a substitution. And then we're going to convert rectangular to parametric. Okay? So we'll start with the rectangular equation, y equals 1 minus x squared. Okay? And we're going to convert convert the rectangular equation to a parametric system using a given parameter. Okay, so here's the trick. When it comes to converting rectangular to parametric, all right, we must be given additional information. So right now, we don't have enough information to convert from rectangular to parametric. Or I should say we do have enough information, but we have too many options available to us. Okay? So when you have a question like this, when you're given a situation like this, and you're converting from a rectangular, y and x only, to parametric, y and x equal to t, you have to be given an initial relationship. Okay, so for example, we'll use the parameter t equals x. Okay, we'll use the parameter t equals x to start out. Okay, well, if the parameter is t equals x, what's our equation for x? It's just t. That's it. Okay, it's just t. Okay. So again, we have x equal to something with respect to t. Our equation for x is just going to be x equals t. If t is x, that means the equation for x is just x equals t. Then the equation for y, what's it going to be? If in rectangular coordinates it was 1 minus x squared, in parametric, what's it going to be? If t is x. Yeah, done. 1 minus t squared. Very good. Exactly right. Okay. So this is a very simple conversion here, right? It's so simple, maybe it's tricky because you're like, wait a minute, what? Okay, maybe it's so simple, but it's tricky. But the idea is we're told the parameter is going to be t is x. So that means our equation for x has got to be just t, right? And then since y is equal to 1 minus x squared, we can just plug the t in for the x there. So y then is going to be 1 minus t squared, and there's our parametric system. So if you were to graph this in rectangular coordinates, that would result in this equivalently in parametric form. It would give you the same thing. So in essence, right, we kind of have always been doing parametric. In a sense, we've always been doing parametric. It's just that x is the parameter t. X and t are the same thing. That's the parameter. Okay, so we kind of always have been using x as the parameter. Now we're introducing t as our new parameter, the thing that changes, our independent variable, and that t affects both the x and the y. Okay, let's try another one here, see what happens. Let's see, the parameter is t equals x minus 2. Okay, t equals x minus 2. So if the parameter is t equals x minus 2, what's our equation for x going to be in terms of t? If t is equal to x minus 2, that means x will equal what, Matt? T plus 2. Very good. Yeah, you just got to solve this little equation here for x. Add 2 to both sides. Boom. X is t plus 2. Okay. And so that means y then, which is 1 minus x squared, will become 1 minus t plus 2 squared. Y is 1 minus x squared. Use y then is t plus 2, or 1 minus t plus 2 squared, which you can then simplify. You can leave it like that, or you can simplify it, since we can multiply that out. So it'll be minus t squared plus 4t plus 4, which is then negative t squared minus 4t minus 3 when you combine everything together. So there's your system. Okay, so we can also graph x equals t plus 2, y equals negative t squared minus 4t minus 3 parametrically, and it'll be the same graph as this right here. Okay. So there's really an infinite number of possibilities when it comes to converting rectangular to parametric. Okay. You can pick any parameter you kind of want there for x. You can have x kind of be anything, and then you just substitute that in, and you get the y. Okay. All right. So, any questions on that? That's all I got for you. I want to give you guys an opportunity then to get started on the assignment. Okay, you have a good 35 minutes to get started on this homework, so that'll be a good amount of time there, I feel like. Okay. definitely want to make sure that you get some practice with this, because this is the only day we're spending on parametric. Tomorrow we're jumping right into polar, okay? So I had to make sure I got all that done first. If you're taking calculus ABC, you will see parametric again. Okay, we'll show up again. So that's why we show it in the first place here.